This video provides a balanced comparative analysis between additive and conventional manufacturing, exploring advantages, limitations, and economic trade-offs. In this video, we will distinguish between manufacturing processes, identify design freedom advantages, acknowledge systemic limitations, and master cost modeling for scaling production. Let's begin by looking at the paradigm shift in industrial production and design. Conventional production relies on removing material or forcing it into molds, requiring significant upfront costs. Conversely, additive manufacturing builds parts layer by layer from digital data, decoupling production costs from geometric complexity. This table highlights key distinctions. Additive manufacturing offers toolless production, cost independence from complexity, lower material waste, and significantly faster setup times compared to conventional methods. Next, we explore the specific advantages of additive manufacturing that are revolutionizing modern engineering. A major advantage is that complexity is essentially free. While traditional machining struggles with intricate channels or organic shapes, additive manufacturing builds these structures just as easily as solid blocks. Additive manufacturing also enables generative design. AI algorithms can compute the most efficient, organic, bone-like structures that are impossible to produce with conventional casting or milling, leading to massive weight reduction. Thirdly, additive manufacturing eliminates physical tooling. By removing the need for expensive steel molds, it lowers the barrier to entry, allowing startups and niche markets to launch products without huge capital expenditures. With zero upfront tooling costs, iteration becomes much faster. Engineers can modify designs and print them the very next day, drastically shortening time to market. Additive manufacturing also enables mass customization, allowing for individual bespoke products at scale. A prime example is in healthcare, where patient-specific medical implants are printed based on MRI or CT scans. Multiple unique parts can be produced simultaneously without any extra tooling penalty. Another significant advantage is part consolidation. Designers can combine complex multi-part assemblies into a single, unified structure, increasing reliability by removing potential failure points. The GE aviation fuel nozzle is a classic case study. Previously made of 20 separate components, it is now printed as one, resulting in a part that is lighter, more durable, and easier to supply. Finally, additive manufacturing offers unmatched lightweighting potential. By placing material only where it is needed for structural integrity, engineers can reduce weight by up to 60%, a critical factor for the aerospace and automotive industries. Beyond surface topology, additive manufacturing allows interiors to be filled with complex microlattice structures. These mimic natural forms like bone, providing incredible stiffness to weight ratios for energy absorption or medical integration. Additive manufacturing also enables digital inventory. Instead of warehousing physical parts for decades, firms can store digital files and print components on demand, reducing working capital to nearly zero. Finally, this technology enables distributed manufacturing. By using networks of local microfactories, companies can print at the point of need, drastically cutting logistics costs and creating resilient supply chains. Now that we have covered the advantages, we must address the limitations of additive manufacturing and the engineering and economic barriers to its universal adoption. A primary limitation is material anisotropy. Because parts are built layer by layer, the bonding along the z-axis is inherently weaker than in the xy plane, requiring careful part orientation and thermal treatment to manage. In metal additive processes, rapid heating and cooling cycles create significant thermal gradients. This traps residual stresses, causing potential warping or cracking, and results in a microstructure that differs significantly from forged or cast materials. Additive manufacturing also faces challenges with surface finish and tolerance, as built parts often require secondary machining for mating surfaces, and powder-based methods cannot match the precise tolerances of conventional CNC machining. The stair-stepping effect is another common artifact, where curved surfaces appear segmented due to layer thickness. Reducing this effect by using finer layers exponentially increases build times and associated costs. Build size is also constrained. Most industrial metal printers have limited chamber volumes, and scaling these systems is difficult due to the complex energy and thermal management required for larger parts. Large-scale additive manufacturing poses risks, as exceeding chamber size requires segmenting parts. Additionally, larger print failures are costly, potentially wasting days of expensive machine time and materials. Production throughput remains the fundamental barrier to universal mass adoption for many industries. Additive manufacturing faces a cycle time chasm compared to injection molding. While molding can produce thousands of parts per hour, additive methods are bottlenecked by point-by-point laser processing, resulting in much slower production. As this comparison shows, even with multi-laser systems, additive manufacturing is orders of magnitude slower than conventional formative processes, restricting its use to low or medium volume applications. Consistency is also a challenge. Machine-to-machine variance and powder degradation over time can introduce metallurgical flaws, making rigorous certification for sensitive industries like aerospace difficult. Finally, the burden of post-processing, often called the dirty secret of additive manufacturing, is a critical factor that impacts overall project time and costs. Beyond printing, metal additive manufacturing requires extensive post-processing. Support structures must be manually removed. Thermal treatments like stress relief and hot isostatic pressing are needed for structural integrity, and critical surfaces often require final CNC machining. These hidden costs are significant. While the print is automated, tasks like powder removal and polishing are highly manual. Consequently, post-processing can account for up to 60% of a component's total cost. Next, we will explore the essential components of cost modeling in additive manufacturing to better quantify these economic realities. A complete cost model must account for direct costs, including material consumption, energy usage, machine depreciation, and labor. Indirect costs, such as facility overhead, software licensing, and quality assurance, must also be included. In metal additive manufacturing, machine depreciation is typically the largest cost driver. Because these systems are major capital expenditures, achieving economic viability demands high, continuous utilization. Given the massive initial investment, industrial printers must operate near 90% utilization to amortize costs effectively over their 5 to 7 year lifespan. If machines sit idle, the hourly depreciation rate spikes, making the final parts uncompetitive. The fundamental cost equation in additive manufacturing shows that build time is directly proportional to part volume. Therefore, production costs are primarily driven by the volume of material melted, regardless of the part's shape. Material costs are also a major factor. Specialized metal powders and high-performance resins are significantly more expensive than standard manufacturing feedstocks, which can severely limit the technology's application in low-margin industries. Operational overhead is further increased by the need for skilled engineering. Designing supports and tuning build parameters require specialized expertise, while the high energy demand of industrial lasers increases the carbon footprint per kilogram produced. To standardize these factors, the industry relies on the Hopkinson-Dickens model for comparative economic analysis. This model provides a framework for allocating machine costs based on volume and nesting density. It allows engineers to compare the flat unit cost of additive manufacturing against the decaying unit cost curve of injection molding. The Hopkinson-Dickens curve illustrates the break-even point. While injection molding has high initial tooling costs that drop rapidly with quantity, additive manufacturing offers a relatively constant unit cost, defining when each technology is most economical. Let's examine how this break-even analysis shifts based on quantity and geometric complexity. At low volumes, additive manufacturing is often the most economical choice because it avoids expensive tooling. However, for high-volume consumer goods, the lack of economies of scale makes additive manufacturing a liability compared to traditional mass production. In conclusion, understanding the matrix of quantity versus complexity is vital for strategic manufacturing decisions, ensuring the right process is selected for every unique application.